Right. Good afternoon, everyone. Thanks very much for staying right to the end to listen to us. We hope to make it worth your while. My group and Irene's groups have been collaborating for the past few years, actually, on a pretty exciting project to take the research that she did as part of her PhD thesis and expand it to a fully fledged open source project within the CNCF. So that's what we're going to talk to you about today. As a brief overview, we'll provide some context to motivate why we did this work and the problems that we believe exist and need to be solved. Then we'll look briefly at the different kinds of skills required to build and run modern applications, and we'll briefly touch on a broader effort to create a full distributed operating system, and then zoom into the most interesting part of it, which I think is the microservice runtime system. Irene will describe in some detail how all of this stuff works and some of the interesting findings from her research. And then to convince you that this is not all smoke and mirrors, one of my colleagues, Venu, will give us a demo of some of the stuff in action. Hopefully that'll help you to some of this stuff is a bit abstract and difficult to wrap your head around, so demos can be useful to illustrate what's possible. We're pretty short of time. We've got a lot of material to cover, so I'm going to move fairly quickly. And we should have some time, being the last session, I guess we'll have some time to overlap with Q&A. Right, so long time ago, applications were pretty simple. They typically supported a single user, ran on a single machine platform, and only ran on one operating system, for example. These were things like text editors and document viewers and calendars, and even browsers actually were, to some extent in that category. And life was, pretty good. Single machine operating systems work fairly well. Linux, Windows, Mac, etc. Android even. All of these provide, great abstractions for those kinds of applications, local processors, virtual memory, file systems, locks. All of these things are kind of indispensable when writing applications on a single machine. And for the most part, if you wanted to build an application, you could do it in one or maybe two languages, and everything was good. The problem is that relatively suddenly, everything changed. So cloud computing happened. Everybody moved to smartphones, mobile-first strategies, etc. Ubiquitous connectivity happened with high-speed, high-bandwidth networks, and suddenly everything changed. So the types of applications changed. Suddenly we had, social media and these kinds of things. But in addition to that, all of the stuff that previously was single-user also became, collaborative, multi-user applications. None of this is surprising, but it's important to note that there's some fairly big differences in the nature of the applications and the kinds of development that you need to do. And even today, my aquarium at home has, Raspberry Pi installed in it, and that thing talks to the cloud and controls the temperature of my fish and a variety of other things. So it really has become pretty ubiquitous. Now, in practice, I forgot about my animation. So these things suddenly get very complicated. You've got lots of machines, lots of people, sometimes not very reliable network connectivity, and you've got to try and write applications that run in this environment. And unsurprisingly, people are tearing their hair out. So one of the reasons why this Cloud Native Computing Foundation exists is because this stuff is hard. Kubernetes was obviously one of the first big tools that people use to try and wrestle with this complexity. Now you can partition your applications up into containers and use things like Kubernetes, but it's still relatively difficult. So along came essentially the CNCF, containers, Kubernetes, microservices, etc. And this was definitely a big step in the correct direction. So we could, as I said, decompose our applications into independently deployable containers. And a lot of this work sort of started in the early to mid-2000s, particularly at companies like Google and Amazon, and has become reasonably mainstream these days. Most of all the things on this slide, and things have got better. So the reason you're here is because you know that all this is good. Programmatically, orchestrated, declaratively driven configurations. Different languages can be used in every single container. You can hook these together with things like Linkerd and Envoy and Istio. And you can, your SREs can run these things and your developers can develop them. However, the problem is somebody's still got to write the code that runs in those containers. And it turns out that that is actually extremely difficult to do and very difficult to do reliably and in a way that actually gives you the application the properties that you want. And it can be done, and companies like Google and Amazon have been doing it for a very long time. But they also have, somewhere around 100,000 pretty good software engineers, and they spend a lot of them building these resilient, scalable systems. Problem is that your mere mortal application developer doesn't necessarily, or your company that needs to build some end-user application, it doesn't necessarily have tens of thousands of the best distributed system software engineers in the world. So the kinds of problems that people run into very frequently are things like distributed concurrency, synchronization. How do you, make unreliable networks look reliable from a remote procedure call point of view? How do you handle faults, disconnections, reconnections, retries, leader elections, sharding for horizontal scaling? All of these things are actually pretty complex distributed systems problems that we're forcing application developers to have to understand and use. And as I mentioned, some areas of these have been partially fulfilled by things like service meshes, for example. But there isn't really a single platform that you can sit down at and write an application and know that you've got all the primitives that you need in order to build a good distributed application. And if you contrast this with a single machine operating system, something like Linux, everybody assumes that every single machine operating system, whether it's Linux, Windows, Android, etc., is going to provide virtual memory, file systems, locks, these kinds of things. But we don't actually have the equivalent things for distributed systems are the ones on the list on the slide. We don't have a standard implementation on every platform, and we think there should be one. So, not surprisingly, these are distributed system problems. These are the things that Andrew Tannenbaum and these kinds of people have been teaching computer science nerds for quite a few decades now. In the same way that when you study computer science, you learn about how virtual memory managers work and you understand how TCP sliding windows work. But we don't expect application programmers to actually write TCP sliding windows in their applications or decide which memory needs to go on disk and which needs to go in RAM. That should be abstracted away, which at the moment it is not really in distributed systems. So the question is, what do we do about this? So we clearly need people to solve these problems who are not necessarily application developers. And they are pretty specialized. So I just want to do a quick diversion here and talk about this terminology that I'm using. An application developer is not necessarily something that everybody understands, certainly not a standard term in the industry. So I just wanted to make it clear in my mind what I'm talking about here. So I think there's a large amount of very necessary specialization that's developed around this area. So on the left-hand side, you have application developers. So these are the kinds of people who know a particular application domain very well, whether it's travel, finance, banking, social networking, whatever. They know what their systems need to do. They know what their customers want. They know what functionality they need. They don't really give a hoot about Paxos or distributed systems algorithms or exponential backoffs or TCP sliding windows for that matter. Then in the middle there you have system developers, what I've called system developers, and in particular distributed systems developers. So these are the kind of people who are really interested in understanding and solving hard distributed systems problems. But they're in extremely short supply. They also cost a very large amount of money typically. And more problematically, they don't actually understand your business needs really. And typically they're not that interested in them. They're more interested in distributed systems problems. And then of course we have the SREs or DevOps people. And these are also very specialized, also very expensive typically. And these are the people that understand how your actual application behaves in real life. When your customers hit your application, what happens? What do the sharding systems look like? What do the overload situations look like? How much capacity do you need? All these kinds of things. Once again, they're not necessarily distributed systems experts, and they're certainly not necessarily application domain experts, but they do understand how to run systems well. And so I think it's very useful to understand these distinctions. Of course, in some cases, you can get individual people who have all of these skills and perhaps fulfill all of these functions. But my experience has been that, SREs are exceptionally good at running very reliable systems, and application developers should be very good at understanding their application domain. And we shouldn't try and force people to kind of be jack of all trades and not very good at any of these things. So, what do we do about this is the question. So we don't have time to go into all the details, but we have this umbrella project which we've called Amino.OS. Basically, we think that ultimately what we need is a distributed operating system. And we think that will probably be comprised of at least a few subsystems, one of which needs to manage distributed microservices. And that's what we'll be focusing on today. We think that, synchronized distributed memory, shared memory of some sort is also super useful, and we have some prototypes of systems that we think will be useful there. Obviously, persistent storage, transactional, variably consistent persistent storage is very useful, and security and privacy obviously is very important, but also very difficult actually in distributed systems. So those are the areas that we think we need to tackle. We're only going to speak about Amino.Run, but I just wanted to give you a little bit of context of where this project fits in. So again, I'm not going to dwell on the details of this slide, but just to let you know that we think that what we really want to be thinking about is distributed cloud-native applications as a thing. That run, that we don't have to go and, decide which pieces need to go onto which machines. The operating system should take care of some of that stuff. We need a unified system that provides these microservice runtime environment, memory management, storage, etc. And it needs to run across all operating systems and be programmable from all programming languages. Otherwise, we don't really live up to the promise of this new world. This is a lot of research has been going on for several years at the University of Washington, and Irene will be stepping up in a few moments to dive us into some of the work that she did with her team there. And then after that work was done, and around about the time when Irene was publishing her PhD, I came across it, and we decided that this was worth turning into a big open source project that people could actually use on an ongoing basis. The research wasn't intended for that purpose. It was really exploratory to figure out, what the space looked like and what we needed. So in particular, there are academic papers and things floating around which cover a lot of this material. Some of the terminology, just to sort of warn you, is different. So over time, we discovered that certain terms we used were confusing. We, for example, renamed this Sapphire system to Amino.Run, and a variety of other things. So if you see contradictory terms floating around, you'll hopefully understand the origin of these things. Right, so we're going to look at what the goals were, the architecture, how it works, in particular these deployment managers, which are a pretty key part of the Amino.Run system. Some of Irene's experience in evaluation, they did some tests and came up with some pretty interesting observations and data. As I mentioned, Vanu's going to give us a demo to prove it's not all smoke and mirrors, and hopefully if we manage to keep everyone awake for long enough, we will manage to have a Q&A session at the end. So our goals, the primary goals that we had were that we want to separate application logic from code, from deployment code, so that different people can do different things. So that goes back to my slide about SREs versus application developers versus system developers. And then we also want to allow these people, particularly the SREs and system programmers, to choose deployment approaches that meet the application requirements and be able to change these deployments without modifying the applications. So we don't think that it's a good idea for applications to actually know anything about sharding or load balancing or error recovery or any of these things, because they're not really related to application logic. We would prefer to separate that out into different part of the system which can be dealt with by expert programmers in those domains and run by people who know what they're doing with them. In addition, of course, we want it to be super simple to understand and use, must be high performance, and it must support all the different programming languages that everybody knows and loves. I've been around long enough that I've come to the conclusion that trying to convince someone to use a programming language they don't like is not very successful in practice very often, so I decided not to try and do that. And we definitely don't want to reinvent any wheels or compete with any existing systems that solve some of these problems well. So there are service meshes out there. We're not trying to put service meshes out of business. We just want to create a sort of a cohesive platform that people can use and plug in the service meshes of their choice underneath. Right. So I think around about now is when I start handing things over to Irene. And I'm running out of time, so let me think what else I want to say before I hand over to her. I'm going to skip a few slides here. So we'll give you an overview of the architecture and then describe all of these layers in a little bit more detail. At the top, we've got the application itself, which runs in a uniform environment that spans across mobile devices, cloud servers, and edge devices. And at the bottom, there's a deployment kernel that runs everywhere. The application does and provides a uniform environment for applications with basic deployment services. And it's very convenient and easy to run and manage the deployment kernel layer and therefore everything on top of it on top of Kubernetes. And we do that. That's our sort of default deployment mechanism. But it's not required or fundamental to Amino itself. And just to give you an idea of what a in-practice deployment might look like, and I apologize for the not very good color scheme here. But basically, we have this big distributed cloud application broken up into microservices, and obviously each one of those microservices might be further decomposed into other modules. Each one of these microservices is run by one or more deployment managers in that layer in the middle there, and all of these run on top of essentially a distributed kernel, which provides all the heavy lifting, the thing that moves processes around and intercepts various different system calls. And using this kind of approach, it becomes very straightforward to, for example, automatically migrate microservices to optimize for any given property, latency or power consumption, anything like that. And we want to do all of this with support for multiple languages. I'm going to skip over most of this slide. What I would like to mention briefly before handing over to Irene is that we did quite a bit of work to support multiple languages, and we used a thing called GraalVM, which some of you may have come across. I'm not going to go into detail. We definitely don't have time, but I wanted to just mention that it's a high-performance polyglot, meaning multi-language virtual machine in the sense of a JVM, not in the sense of an OpenStack virtual machine. And it provides support for both ahead-of-time compilation and therefore native execution, or just-in-time compilation. It's embeddable in other environments, so you can actually embed it inside a database to run these things. You can embed it inside the OpenJDK, or you can run it standalone. And the particular thing that it buys us is the ability to, one, produce different parts of the application in different languages and yet be able to easily transfer data structures and things like that between the different parts of the language. But also the kernel, the deployment managers, and the application can also be run in different languages without the language boundaries getting in the way. And just to be clear, some of these diagrams are going to show all these layers and pieces of software. This stuff all gets compiled away into a single binary, a single process. So you don't need to worry too much about, inter-process communication and network connections and all that stuff, other than obviously between machines. But wherever you have multiple of these layers on the same machine, they all get compiled away into nothing, effectively. And with no further ado, I'm going to hand over to Irene.
Hi. So Quinton told you a bit about what the Amino runtime's goals are and what it's capable of. What I'm going to talk about is sort of the nitty-gritty technical details of how it actually does all of this magic. So the key idea behind the Amino runtime is that we divide the runtime into a deployment management layer and a deployment kernel. And the deployment kernel is the very lowest layer oh, these are our microservices, is the very lowest layer of the Amino runtime. And what the deployment kernel does is it does essentially those best effort mechanisms that you need for running any microservice. So it provides instantiation of your Amino microservices. It automatically replicates them, tracks them, it can move them, and it can also find your Amino microservices. So you can essentially make a call transparently from any Amino microservice to any other Amino microservice without having to, do a lot of complicated lookup and RPC management. Finally, the most important task of the deployment kernel is actually to manage and distribute deployment managers. So deployment managers, in essence, they live on the deployment kernel servers, and they live in a layer above the deployment kernel, and they provide guarantees that are in addition to these basic microservice mechanisms that you might want. One of the things I say about the deployment managers is that they're sort of the magic sauce. They're libraries that make all of the magic happen for all of these complex coordination tasks that you might want to do across and between your microservices. So deployment managers actually work by interposing on RPC to and between microservices. And what they can do is they can do things like create multiple copies of a microservice, and then every time that microservice receives a call, it will route the call to all of those copies rather than just one. It can also do things like shard a microservice and then route RPCs to that microservice to the correct shard. And then finally, microservice calls and events, this interposition that these deployment managers are doing, they're completely transparent to the application, right? They're completely transparent to the microservices themselves because they happen before the RPC reaches the microservice. And so that means that you can actually, as an application programmer, easily choose and then change your mind about what kind of deployment manager you might want. For example, you might start out having just a single copy of your microservice running, but then decide you need to later shard it. And this can be done without changing any of your application code. The other thing that we can do with deployment managers is arbitrarily combine them. So we would obviously like to be able to have shards that are replicated, replicas that you might be able to do transactions, distributed transactions across, and so on. So the way that the deployment management layer works is that for each microservice, the programmer chooses a single deployment manager. So you might choose for some of your microservices, say that you need to replicate for fault tolerance, you would choose a replication deployment manager. For some of your other microservices, you might choose things like code offloading if you want to move your code somewhere where there's a more powerful machine, or maybe one that has a GPU or some other service that it's able to offer. We offer a library of deployment managers that covers lots of categories of what we expect to be standard problems for application programmers to solve today. So things like caching, checkpointing, replication, sharding, and scaling. We have a selection of libraries of deployment managers for each category, so not everyone has to do caching in the same way. You can do caching using a lease, you can do caching using some sort of timeout, you can do caching using an explicit lock. So this is a list of some of the deployment managers that we have built. We continue to expand on them, and the deployment manager library is very much extensible. And this is entirely due to the way that the Amino runtime is architected. So I'm going to talk next about how each deployment manager actually works, to give you an idea about how SREs or these distributed systems people can actually build additional deployment managers based on their needs or their research. So the deployment manager API takes each deployment manager and splits it into 3 components. So each deployment manager must consist of some server-side code, which the Amino runtime will co-locate with the microservice itself, some client-side code, which the Amino runtime co-locates with the callers of the microservice, and then a centralized group coordinator component, which is located on a fault-tolerant service that's provided by the Amino runtime. So to make all of this a little bit more concrete, I'll explain exactly what happens. So you write code for each of these deployment managers, and the deployment managers invoke the code automatically on each RPC. So you start out with your microservice, right? It runs on some server somewhere in your Kubernetes container. Then you decide that you want to replicate this microservice. So how do we go about doing that? Well, we have a single copy of our microservice, which we place in a Kubernetes container. And then we create a server-side deployment manager that runs next to it on the same deployment, on the same kernel server. Then we can create another copy, which gets its own copy of the server deployment manager. So these are just code that get invoked by the Amino runtime on the deployment kernels when the microservice receives an RPC. So these deployment managers, they can talk to each other within a single address space. So essentially, the Amino runtime is providing transparent RPC between the deployment managers, between the components of a single deployment manager. Then to reach each microservice, each application goes through a stub in order to call the microservice. This is where the magic happens of the Amino runtime deployment kernel, where it looks up where the microservice lives and makes the RPC to the microservice depending on where it's been deployed. And so with this stub, we co-locate a little bit of code that we call the piece of the deployment manager that's the client component. So each stub gets its own bit of client-side code, and that code gets invoked every time another microservice makes a call to this microservice. And then when the call reaches the server or the Kubernetes container where the microservice is running, first we invoke the server-side deployment manager before we upcall into the application itself or the microservice itself. And then finally, all of these can communicate with the centralized group deployment manager, which is we consider a centralized and fault-tolerant component. So this can do things like choose leaders for your replica group. It can decide, who holds leases for how long, and other things like that. So the people who write deployment managers don't have to handle this kind of stuff themselves. So I'm going to be a little bit more detailed about what happens when you actually make an RPC to a microservice that's running on top of a replication deployment manager. So in the beginning, the deployment manager is going to instantiate 3 copies, each in separate Kubernetes containers, of the microservice. Then, whenever we start actually running the microservice, we are going to choose a leader for the microservice out of the 3 replicas. And any calls that come from inside the application are actually going to be forwarded to the leader first. The server deployment manager will then replicate that call to the other copies and upcall into all 3 copies at the same time before replying with the response to the client. And so in this way, essentially, by interposing on the RPC to the microservice, we're able to transparently provide replication, essentially state machine replication, without having to actually write that explicit code into the application itself. So we can do something similar for offloading. So this is where the microservice might be running on some node that doesn't have as much computational ability as it might like. So in the Amino runtime case, this could actually be an edge node or a mobile device. What we do then is we essentially just create another copy of the microservice on the cloud, and we forward calls to the local microservice that might be on a slightly underpowered node. And if we find that the performance is not good enough, the deployment manager can actually transparently forward the call to the instantiation that it's made on a beefier cloud machine without having to interact with the application code at all. And so it's able to do this completely transparently under the covers. We can do the same thing for caching. So this is perhaps where the latency is too high to your microservice, and you want to move the microservice closer to you. So essentially what happens in the caching deployment manager is sort of an inverse of the offloading one. We have some master that's running on a cloud server, but that we decide the latency is too high. So then instead, what we do is from the callee, the other microservice or mobile device that's making the call to this microservice, we actually create a copy of the microservice and cache it inside the client-side deployment manager. So in that case, we can now have much lower latency access to our local copy of the microservice. But of course, now we have to keep that microservice consistent or coordinated somehow with the master microservice. So hopefully this gives you some idea of how these deployment managers can transparently under the covers do a lot of the coordination that applications today would normally have to do in the application itself. I'd like to note that we can actually also do much more sophisticated stateful object migration under the covers without letting the application know. Because every RPC is done through the Amino runtime, the Amino runtime has actually the ability to move microservices wherever it would like based on metrics like minimizing latency between the microservices or minimizing throughput or optimizing your power usage. Right? And you can imagine that this becomes actually a pretty complicated distributed problem because you want to do a full optimization with all of the information that you have of how much computation each node is doing and how much communication there is between the different microservices. So this is actually something that you'll see in the demo in a minute. So we can also compose deployment managers. This is essentially done through chaining. So every time an RPC is made, we go through a chain. We could potentially go through a chain of deployment managers in order to achieve all of the properties that we want for a particular microservice. As you can imagine, this does eventually get pretty complicated, which is actually why it's important that application programmers don't have to do this. And it's done under the covers with configuration by SREs or distributed systems programmers. All right, so to wrap up, I'm going to talk a little bit about some experiments that we did with our initial prototype of the Amino runtime. We ran our experiments on a series of Nexus devices and cloud servers connected through Wi-Fi and a 4G connection, basically. So the first thing we're going to look at is what happens in a peer-to-peer multiplayer game when we use different Amino deployment managers to place the microservices in different ways. So initially, so the x-axis here gives the different deployments, and then the y-axis gives you the latency of making each move in the game. These results are probably about 5 years old, so take them with a grain of salt. So the first thing that we tried was actually just placing the microservice in the cloud and having the two clients share and access the microservice together. So that gives you roughly even latency for both players for both read and write. Now we can actually just dynamically move the microservice if we would like to one of the player's devices. So in this case, we've moved it to player one's device. So this has been done without any application code changes whatsoever. We're just dynamically moving or migrating the microservice to the user's device. And you can see that player one suddenly gets much better performance, and player two sees a slight increase in its performance. Now, alternatively, we can deploy the microservice in some peer-to-peer way where each player's device actually hosts a copy of the game or microservice by itself. And so in this case, you can see that both players are getting great read latency because they're able to read their own local copy of the microservice. But when they have to write to both their local copy and their opponent's copy and update all of the players. And so in this case, writing becomes much more expensive. We can see similar results for taking a physics engine, basically for a mobile game, and moving it between running on the mobile device and running on the cloud. So when we have a phone, we are able to run the physics engine on the phone, but at quite a high expense. If we have a tablet, we have slightly better performance, actually, and so our physics engine is able to run much faster. Alternatively, we can actually move the physics engine as a microservice onto the cloud, where the performance sort of shifts, right? So most of the performance is going to be spent communicating with the remote microservice, and then the cost of actually running the physics engine is going to go down significantly because it's able to run on a bigger, beefier cloud server. And then when we run over something like a 4G network, the network becomes even more expensive. And so you might decide to change your placement of these microservices based on whether the user is using Wi-Fi or 4G and whether they're moving around. So that's pretty much it for all of the details about how the Amino runtime works. I will give it back to Quinton to summarize and talk about what the next steps are for this project. And then we still have negative 2 minutes for the demo.
Hello. Yeah. So yeah, we've run terribly over time. I'm sorry about that, but we're nearly done. And given that there are no more talks, I guess that's not too serious. So yeah, I think we've looked at the summary. There are numerous things we would still like to do. This stuff is usable at the moment, but I wouldn't deploy any banking applications on it just yet. But it's getting there. We also there's some limitations to the state migration. So for example, if your application has state that sits outside of your microservice, an external file or something sitting in the operating system, that doesn't magically migrate with your microservice. So we can do some pretty straightforward things to make that work better. There's some rough edges between certain combinations of languages. We support a large number of languages, and depending on the permutations, there's some slightly funky things that happen, which we'd like to clean up. We would like to build some more plugins for external systems, things like etcd and TIKV and Istio and these kinds of things, which clearly can be well used inside a deployment manager. And then we're also very interested in federations and disconnected edge computing scenarios. So we've done some work on that area, and we've run some things in those kind of contexts, but we're not totally sure that everything works. The original design was not explicitly created for that. All right. Feel free to get involved. This is all open source. We just open sourced it literally like 1 day ago. There's a Slack channel, there's a website, there's a GitHub repo. You can go and have a look there, and certainly get in touch with us if you're at all interested in this stuff. And I would like to then hand over to Venu, who's going to give us a little bit of a demo, as I said, to hopefully show everyone that this is not just smoke and mirrors. What I have to do is figure out how to mirror the displays, and we were not brave enough to do a live demo given how flaky the network is, but here we go. So you can maximize it there, and you can push play there, and you can talk into that thing. Just check that.
Okay, I'll be giving the demo on automatic object migration now. It's for face recognition microservice. Left down one is an object monitoring system. It's a part of DK. And the right above it, run KS1, what you're seeing is a kernel server. So I'll be, and the right side top one is a cloud kernel server. And the right bottom one is an application. That is the place where we run the client. So we are starting an OMS now. Starting a kernel server gets registered to the OMS. Now we are running the cloud kernel server. We have more CPU capacity there. So microservice will be migrated from the application client side to the kernel server. It migrated just now. Frame rate is increasing now because it has more CPU power. We have reached 11 of frame processing per second. If we see, it has improved much when we run it on the kernel server to application client. Again, when we run it on the cloud kernel server, it has reached 12 now. So better the CPU power is, it is migrating there. Yeah, you're done. You have any questions?
Thank you very much for staying till the end. We're around for Q&A. If anyone has any questions or anything they want to discuss, we're happy to take questions. Go ahead, Mike.
The running process that's...
Yeah, that's a good question. So the way it works is the running process, you can imagine, it's actually a class, an instance of a class that is being migrated, and that has state in it. So what we do is we freeze the state, we move the state to the other side, and then we load that into a virtual machine with that state, and then we carry on running. And because we have, built into the deployment manager layer, we have things like retries, and there may be replicas of this thing. So the system takes care of making sure there are no failed RPCs, et cetera, in that process.
Awesome. Sure, it was a lot of work.
Hello. Any other questions?
Well, a first small question. I noticed from 25 years ago when I was a student, and I was taught about this by Andrew Tenenbaum. But
you
how
have the
is
right
it
accent.
now finally in production? What took so long? Do you have an opinion about it?
Yeah, that's actually a very good question, and one that comes up quite regularly. We've seen these kinds of things for a very long time, DCE, and there are lots of things, in the 90s that did this. I think there were, a combination of factors that just made them not become ubiquitous. We didn't have public clouds in those days. We didn't have mobile devices. We had warring Unix vendors trying to outdo each other. We had standards committees trying to come up with standards for these things. And I think no one of those things is necessarily explains why they didn't take off. But I think in combination they just prevented this from becoming ubiquitous. I think the other thing that is pretty important is there was this kind of notion that you could just take any object-oriented program and just scatter the objects all over the network, and it should be transparent. And we discovered that doesn't work. It explicitly does not work. You need to tell the programmer that this is a microservice, this is remote, this is going to fail, it does need to be replicated, and it's fundamentally different than an object that's on your machine in your same physical address space. If you try and blur that, then things just don't work. So we explicitly don't do that. Cool. Anything else? Thank you very much again.